Welcome to RISE Learning Machines seminars. I am Olof Mogren. I'm a machine learning researcher here at RISE. RISE is Sweden's public research institute with nearly 3,000 people working on a wide array of topics. And this is our weekly seminar on AI and machine learning. This particular seminar is organized in collaboration with Climate AI Nordics, a network of researchers in the Nordics working on AI to fight climate change. The meeting will be recorded. Let us know if you want to be removed from this recording. And also remember that we have an amazing collection of great talks collected on our YouTube channel, which you can check after this. Today, I have the pleasure to introduce Ghjulia Sialelli, who is a second-year PhD student in the photogrammetry and remote sensing lab at ETH Zurich and an ETH AI Center doctoral fellow. Her PhD topic is around computer vision and remote sensing, and she is also organizer of the AI plus Environment Summit, which is taking place in Zurich later this month, I think, or next month. At least today, we have the topic SatML for a large-scale above-ground biomass estimation. And with this said, I will hand over the floor to you, Ghjulia.
Thanks a lot for the introduction. Just give me a second to share my screen. Okay. Okay. Can you see my slides?
We see the presenter mode.
Okay. What about now?
Perfect.
Okay, cool. Okay. Thanks a lot for taking the time this afternoon to attend this talk, and thanks a lot for inviting me. The topic of today's presentation is going to be SatML for large-scale above-ground biomass estimation. And basically, I'm going to be presenting the research I've done for the first year and a half of my PhD. Now, I just want to start by introducing what I mean by SatML. So it's a term that was coined, or at least used in this paper, which SatML means machine learning for satellite data. And basically, the authors of this paper advocate to treat satellite data as a distinct modality in machine learning with its own opportunities and its own challenges. So that's something that I like to keep in mind, and so I wanted to mention it here. The rest of the title, large-scale above-ground biomass. I'm going to dive into what exactly biomass is in a couple of slides. And what do I mean by large scale? It just means that whatever I'm doing, I want to be eventually able to do it on a global scale. So that's how large the scale is. All right, so just to go quickly over what the next 40 minutes are going to look like. First of all, I'm going to give you some of my personal motivation on why I'm working on this specific topic. Then I'm going to go over my first publication. So we curated a data set specifically for the task of biomass estimation. So I'm going to go over the data set itself, the baselines we set up, and what we learned from the entire process. Then I'll go over our recent efforts to build on those baselines and get better at biomass estimation. I'll mention some inevitable future work because we can always do better. And then I will quickly go over the AI plus Environment Summit that Olof mentioned. So if you're interested in that, please stick until the end. So I don't see everyone. So if you have a question, either like unmute yourself and ask it, or we can also wait until the end of the presentation for the questions. All right. So regarding the motivation, I think we've all heard about climate change, and the latest IPCC report says that now in order to stay below 1.5 or 2 degrees Celsius of global warming, the use of carbon removal strategies is now inevitable. And this set of carbon removal strategies are in part supported by the carbon credit market. So for example, if an airline wants to claim it's reducing its carbon emissions, it can basically pay, for example, for a patch of rainforest in the Amazon that was deforested to be reforested or to be protected against future potential deforestation. However, we know that the carbon credit market is flawed. There have been investigation and reports showing that certifiers are overstating their ability to cut emissions, or that dishonest players are actually profiting off from public lands that they say they're protecting, but they're actually already protected. And that actually contributes, instead of slowing down climate change, it actually causes the risk to exacerbate it because big players that emit a lot think they're offsetting when they're not. So this is a problem. And this is in part due to the fact that we don't have a monitoring system for carbon stocks. And so I want to, in my own little way with my research, contribute towards solving this big problem through biomass estimation, because biomass stocks and carbon stocks are connected. There's a 1:2 ratio between the two of them. So if you have biomass, you also have carbon stocks. So that's my overall motivation for the task. And the way I'm working on it is that I'm leveraging openly accessible and globally available remote sensing data that I'm combining with machine learning methods, because we need to process that huge amount of data in order to learn how to estimate above ground biomass density. So for a formal definition, above ground biomass density is the mass of organic matter above the ground per unit of surface area. All right, so now that you have the big picture, I'm now going to dive into the results from my first publication, which is this data set that we curated specifically for biomass estimation. But before I dive into it, first I want to give you an overview of the existing literature, because biomass estimation is not a new task. There's a rich and varied literature that explored and explores this. So I just want to give you some trends in the field. First of all, I want to introduce some terms so it's easier to follow. What I mean by machine learning based will be that the methods use machine learning for biomass estimation. Non-local geographical coverage means that the study or the data comes from not only one region or a specific country or a specific forest type, but spans a non-local coverage. And by high resolution, I mean that the resolution per pixel should be at least 10 meters per pixel. Right. So some of the products we have, here I want to briefly mention two. The first one is the European Space Agency Climate Change Initiative Biomass Map. So throughout my slides, I'm going to refer to this product a bit. So in the future, I'll just say CCI map from the Climate Change Initiative. And we also have another product that's called the GEDI Gridded Biomass Map for the year 2020. And both of these products, so they're not machine learning based, but both of these products have non-local geographical coverage in the sense that they span the entire or most of the globe. However, they do not have high resolution. The CCI map has 100 meters per pixel resolution, and the GEDI product has 1 kilometer resolution. So this is not high enough to inform specific policies or to have localized insights. Then we've seen the emergence of machine learning-based methods. There are two trends. Some have high resolution estimates, some don't. This is more or less based on what kind of input data they use. So whether they use Sentinel-2, for example, or whether they use Landsat or something else. And also what kind of reference data they use. So do they use field data? Do they use airborne laser scanning strategies, things like this. So some have, some don't have high resolution, but what they have in common is that most of the work so far do not have non-local geographical coverage. So for example, this work is based in the northwestern USA. This one focuses on Congo, this one on Vietnam and Myanmar, this one Finland, Southwest China, and this is for Norway. So there is a rich body of work, and they really provide insights on how we can do biomass estimation with and without machine learning methods. However, the fact that they do not cover the same geographical regions, that they don't have the same data, it makes intercomparison of the methods very hard. I mean, it makes it impossible, basically. And so this is where we wanted to fit in. We wanted to come in with a sort of a benchmark data set for biomass estimation to be able to say, okay, we take this method, and we both train them and evaluate them on the same data set, and then we know which method performs best on like rainforest and which method performs best on temperate forests. But just to be able to have so that we can actually program. Thanks. All right, yeah, I'll just dive right back into it. So our method provides high resolution biomass estimates, so 10 meters per pixel. We have a non-local geographical coverage, which I'm going to dive into in a couple of slides, and our estimates are machine learning based. All right, so now that you know why we wanted to come up with this data set, what is it actually made of? So I'm going to go over what we put inside of it, and starting with our reference data. So because the task we want to solve, we want to be able to do it on a global scale, we also need our reference data to be available globally. And so what we've been using as a biomass reference is the GEDI data product. So I already mentioned GEDI from their 1 kilometer resolution map, which is basically a product that they obtain from statistically aggregating the product that I'm actually going to talk about now. So basically, they put an instrument on the International Space Station, which shoots laser beams at the Earth. And from the return waveform of the laser beams, they're able to infer knowledge about the canopy height, basically. So various metrics, but for example, this would be the top of the canopy height. And from the waveform information and calibration and validation plots that they sourced throughout the world, they're able to estimate biomass from the waveforms. Now, obviously, it's not perfect. There are no calibration plots for a lot of regions in the world, and we're well aware of this limitation. But this is in our opinion, the best we had at this point in time for the task we want to do. So this is what we use for our reference data, and what does it look like in practice? So basically, it's footprints that are sparsely distributed globally, quote unquote, because it's only between this line and this line, just because geographically, that's the only, like the satellite doesn't go north of this. We don't have data north of this. So another limitation we're aware of. Now, what do we use for input data? So what do we learn from? Quite classically, we have Sentinel-2 data that we get from end of 2018 to end of 2020. For each pixel, we also have coordinates. So we apply sine and cosine encodings to the latitude and the longitude to encode their cyclical nature. We also have access to a canopy height map that was produced actually in my lab a couple of years ago. And that estimates the GEDI top of the canopy height. So it's very aligned with what we want to do. And it doesn't only provide the canopy height estimates, it also provides the associated uncertainties linked with the estimation. Then in order to get some more complementary data, because Sentinel-2 didn't penetrate the clouds. We wanted to get some SAR data. So we got it from the Japanese Space Agency. So we have yearly mosaics for 2019 and 2020. And from the same agency, we also get the digital elevation model. Finally, from Copernicus, we get a global land cover map, which is a great product because it's quite detailed in the sense that it has 23 different classes for the land cover, and it also has class probabilities for each pixel. It's produced yearly, technically, but it was last produced in 2019, so that's what we're going with. Yeah, and for all data sources, when they're not natively in a 10-meter resolution, we upsample them to match the Sentinel-2 resolution. And yeah, we crop, reproject, align everything. Right, now regarding the geographical coverage, again, the black rectangle is the GEDI coverage, so we literally do not have data outside of this box. So within this box, the red regions highlighted are the regions/countries that we chose to include in the data set. Now, there's a nice distribution, north, south, east, west, across continents. But this is not the only reason why we chose those regions. The main motivation was that we wanted our subset of regions. We wanted to have its land cover distribution to be as close as possible to the global land cover distribution. So just bear with me for a second. Here on the left, you can see a pie chart that depicts the distribution of the land cover types in a global scale, so for the entire GEDI coverage. And on the right side, you can see the distribution of the land cover types for our subset of countries. So of course, it's not a one-to-one mapping, but this is as close as we can get, and it's pretty close. But what was the reason behind this motivation? Like, why are we obsessed with land cover types? It's because in the past, what we've seen is that when we have biomass estimates, the distribution of the residuals, so like how good we are at estimating the biomass, it varies greatly for different land cover types. From now on, I'm going to use land cover types and biomes interchangeably because we're working with vegetation land cover types, and biomes is just faster to say. So yeah, what you can see here, this is the GEDI biomass values distribution per biome. And on the right here is the residuals. So the difference between the CCI map and the GEDI biomass values. And what you can see is that, first of all, biomass values have completely different ranges depending on the biome that you're considering. And that also stands for the residuals. So we had this idea that, okay, maybe if we focus somehow on the biomes or if we give biome information, the model might learn better. And that was, yeah, and on the right side here, you can see the same plot, but at the scale of our subset of regions. And something that I want to quickly highlight here is that for the biomes here, you can see that some of them are in black and some of them are in light gray. And that's because the ones in light gray are only geographically present outside of the GEDI geographical cover. So they're not present in our data set just because we don't have data for them. So yeah, it's those three. So this is also a limitation we're well aware of. Right. All right, so I went through why we came up with this data set, what it's made of. Now let me quickly, slowly transition to the machine learning part. So we have all of these data sources that we basically just concatenate and that we feed to a model, which outputs dense biomass predictions. So for each input pixel, the model is going to predict a biomass value. And we're going to backpropagate sparsely because, as I mentioned, GEDI is a sparse data source. So we only have ground truth for selected pixels. So we only backpropagate on the ones for which we have ground truth. Makes sense. All right, but what does that look like in practice? So basically, we took our data and to make it machine learning ready, so like easy to train for machine learning models, what we did is that we split it into small patches. So each patch, which is like a training unit, is going to be 25 by 25 pixels, which represents a distance on the ground of 250 by 250 meters. So now that's for the input data. And as I just mentioned, we only backpropagate sparsely. So the way we designed it is that the central pixel will be our ground truth, is the pixel for which we have ground truth. So we have an input patch, and we're going to backpropagate on the central pixel. So we call this the central pixel approach. Is there something I would have?
Yeah, I have a question, if that's
Yeah,
okay.
go for it. I thought I froze again.
Does that mean that you sample these patches around such a labeled pixel?
Yeah, exactly. So the way we created the entire data set, because there are those footprints sparsely located, is that for each footprint, we iterate over them and we crop a patch around it.
Thanks.
So yeah, that's the way we created it, and that's the way we train. Now, something else that's important to know about the data is that it follows a long tail distribution. So if you put the biomass values into bins of like 50 tons per hectare, this is the number of samples that are present in the data set. This is what it looks like. So basically, a lot of our data is in the low biomass values range. And the higher you go in terms of biomass values, the less and less data you have. And that is the natural distribution of biomass values. But this is really tricky for the estimation process. And what you will see later is that it really impacts the performance of the model. So I'm going to get back to that. All right. Now we have the data set. I've shown you the setup for the training. Now, what models did we use? So here I want to emphasize that this was a benchmark paper. So we just wanted to establish some baselines. So we basically looked into a few different models to see their respective capacity. So we had a very basic gradient boosted decision tree. So this is a pixel-wise method. We had a simple fully convolutional network with 500,000 parameters. We had a classical UNet with 10 million parameters. And then we had a more elaborate fully convolutional network that we adapted from the canopy height map paper. And that has 13 million parameters. All right, so now what experiments did we run? What insights did we draw from all of these? The first thing that we did is that we ran an ablation study to understand the impact of the features. We wanted to know, okay, is canopy height enough to estimate biomass? Does adding all of these different input features help in the prediction, or was that just our own personal bias and actually the model can figure it out? So basically what you see here is that each column is a different input feature that we have. So that's going to be height, RGB and near-infrared bands from Sentinel-2, all Sentinel-2 bands, the land classification, the digital elevation model, and that's the SAR data. It's just P2 because it's Allos pulsar to the satellite. And so we ran different configurations of isolated input features, combinations of them, using all of them, just to try to have a feel of what was most helpful for the task. And then what we also did is that obviously we compared the different models between each other. So it's the 4 columns here. And then the numbers that you see here, it's basically the patch size that we feed the model. So as I explained, natively, our patches are 25 by 25 pixels. But because the canopy height paper used 15 by 15 patch size, we also wanted to check, is there a performance drop if we use 15 by 15? Or is it the same? What's actually useful? And for the gradient boosted decision tree, obviously it's a pixel-wise method, so the patch size is only 1 by 1. All right, so now let me dive into the results. First of all, this is a regression task. So the metric we use is RMSE, so lower is better. And the color scheme here just means that higher values are dark red, which goes to light red to light blue to dark blue, which is actually the best. So what we gathered from these experiments was three different things. First of all, for all architectures, adding more input features helps with the prediction. So it is valuable to add additional data. Then the second thing was that more elaborate architectures are able to model better the complex relationship between the satellite data and the above ground biomass. And then the third insight was that having a larger patch size, so a larger context window, also helps with the predictions. So yeah, those were the three insights that we drew from this paper. This is the first table I want to show you. We also have other results. So this brings me back to the long tail distribution. So basically what we can see here is, again, the binned biomass values, and these are the residuals. So for the four models we created and for the CCI map. And what we can see here is a well-known phenomena in canopy height estimation and biomass estimation. It's the underestimation problem, which means that for the low biomass values, where we have a lot of data, we're actually quite good at estimating it. However, the higher you go in the biomass values, the less data we have, the more we're biased towards underestimation patterns, which is a problem because for a very big, like for a patch of a forest which has very big trees that all hold a lot of biomass, you would like to be able to accurately say, okay, this region has a lot of biomass, we should protect it, except that we're systematically underestimating it. So this is a known issue that you can keep in the back of your mind for questions. Something else that I want to show is, again, just showcasing that we have very different residuals patterns across different biomes. And something else that I want to mention is an interesting saturation analysis that we did. So a problem that's related to the underestimation problem is something called the saturation effect. So basically, we hypothesized that above a certain threshold of biomass values, which we don't know what it is, the remote sensing information doesn't reflect anymore the change in biomass. So for example, if the threshold is 380, then the remote sensing data wouldn't be different between 400 and 450, for example, which makes it very challenging to estimate high biomass values. So something we wanted to check, because we know from the table that I showed you earlier that adding additional input features is helpful for the predictions, but is it equally helpful for all biomass bins, for example? And we can see here, so those are the biomass bins again, and this time this is the RMSE. What we can see is that while it's always, again, sorry, and the little dots are the different configurations of the input features. So for example, gray here is only using canopy height, and orange here is using everything but canopy height, for example. So what we can see is that adding additional input features is always beneficial, but it's even more obvious for the higher biomass values. So we hypothesized that maybe including additional input features, data sources that are complementary to each other, somehow helps mitigate the saturation effect. All right. Oh yeah, sorry.
When in this table 2 slides ago, actually, when you added the features,
Yeah.
The RGBN feature is only added to one of the configurations.
Yeah, because since we had all of the bands and we saw that having all the bands was much better than only having RGB and near infrared for
I
the rest
see.
of the experiments, we're like, oh, we'll just put all of the bands. But actually, it could be interesting to only have RGB near infrared for the other experiments because, for example, there are some foundation models that only take RGB near. So yeah, I could run a few more tests.
I missed that it was a subset of the S2O.
Yeah, yeah. Okay, yeah, thanks for the question. All right. And yeah, I wanted to briefly just show a visualization of, okay, what does biomass estimation actually look like at this resolution? So here on the left, you have the Sentinel-2 image. Here is our prediction. And for the sake of comparison, this is the CCI prediction at 100-meter resolution and the GEDI 1 kilometer product that I mentioned. And what you can see here is basically that making predictions at a native 10-meter resolution really allows to pick up local high resolution insights like roads or like dirt paths, stuff like this, that are not picked up at a 100-meter resolution, which means that if we were to using like traditional methods upscale this map, we wouldn't retrieve such details. So there's a real incentive to generate the predictions at a 10-meter resolution directly. Now I said that if you upscale it with traditional means, you cannot get the the high-res insights. So I just want to take the opportunity to showcase the research from a colleague of mine who's actually looking into guided super resolution. So he actually took the 100-meter CCI map and did guided super resolution using a high-res 10-meter Sentinel-2 image. And then you can retrieve some of the local like high-res features. So there are a lot of ways of doing high-res biomass estimation. It's a pretty exciting field to be in at the moment. And yeah, today I'm mostly sharing my view, but I also encourage you to check out more work in the field. All right, so just to wrap up about the data set itself, of course, we want people to use it so it's accessible, both through our GitHub and on Hugging Face. So if you want to check it out, feel free to do so. And now I just want to go over, okay, so we've had this data set with the baselines, but obviously we want to get better at biomass estimation. So now I just want to go over a few of our more recent efforts to build on the baselines. So you've heard me talking about the biome and how we think it's important, but obviously so far we've only provided it as an additional input to the model and kind of like let the model figure out what it should do with it. But we thought, okay, there must be a smarter way, like to go more towards biome-informed learning and not just giving it as an input. And so as a first naive exploration step, we thought of just looking into an ensemble of biome-specific models. So we just take our model, except that we now have a bunch of them, and each of them is specialized for a specific biome. So if we have a patch here, we look at the central pixel or at the majority biome, and then we just feed it into the appropriate model. Now, of course, this is not very parameter efficient because we're looking into 14 different biomes. And so obviously that means that we would have 14 times more parameters to train. And so we weren't super excited about this. So what we actually did is that we looked into, okay, if we take our best model, how much, if at all, can we scale it down and not have a significant performance drop? And what we found was we were actually quite positively surprised about this, is that actually we can scale it all the way to 1 million parameters if we do it in a smart way and not experience a performance drop. So we felt a bit stupid about this because we were taking into the bigger is better hype. So we just started with a big model. but actually if we figured out if we scale it down in a smart way, it also works the same. So at this point, we're still pretty happy to have figured that out, also mostly from a computational point of view. Now my models train much faster, which I'm really happy about. And yeah, everyone using our group cluster is also happy about. So yeah, this was a nice side and actually important insights from this experiment. So going forward, we just continued using the smaller version of the model. And when we evaluated this approach, we found that, oh, we actually, yeah, we do get a performance boost. So again, I'm working with RMSE, so lower is better. So we are happy about that minus here. So yeah, that was a nice approach that worked. Now, obviously, it's still parameter inefficient because even if we have a smaller model, we still need to train 14 different models. Now, obviously, they converge faster because each of them has access to a lower amount of data, but still not the cleanest way to do it. Also a bit impractical for inference because yeah, like how do you patch everything together? And it was more of a proof of concept that confirmed our intuition that if a model has like more specialized insights about a specific biome, probably the thing will work better. So that led us to our next topic, which was looking into film layers. So film layers are a powerful and conceptually, I would say, understandable way of conditioning a neural network's output on a given input. And so basically the way it works is that through like in your model, you're going to add a bunch of film layers. And what one film layer does is that it's going to take the intermediate features of your model and it's going to apply an affine function on it. So there you have a scale parameter and a shift parameter. So it's called a scale and shift operation. And basically this gamma parameter and this beta are computed by the film layer, which learns a function from the input you're conditioning on to this gamma and this beta. So how does it look like in practice? Basically, where before we used to just feed the patch into our model, we now have a film augmented model. So we just add a bunch of film layers. And now we take the biome information as well as the region information, which region is really broad. It's like South America or Europe. But it's just to emphasize that a same biome would behave slightly differently in different regions. And now if we feed the embeddings of the biome in the region to the film layers. So for each film layer, we're going to have a scale and shift operation that's conditioned on the embeddings of the biome and region. So effectively, we're conditioning on the biome and the region. Now that also gave us a nice performance boost that was, I don't have the exact percentage here for some reason, but gave us a comparable performance boost compared to the naive ensemble method, which we're pretty happy about. And something else I want to mention is that beyond this model engineering part, I was also looking into feature engineering because we still had the insight that with the saturation analysis, maybe if we add even more data, we're going to get even better. But now I didn't want to go over the entire data curation process again, so I didn't want to include any more like new data sources. So the question was like, okay, what can we do from what we already have? And the answer is those new features, basically. So we were missing encoding some sort of seasonality in the learning process. So what we did is that we encoded the day of the year of the satellite image, of the Sentinel-2 image, in order to reflect, to some extent, seasonality. I'm also working on implementing vegetation indices at the moment. So NDVI would be the most renowned one, but there are a bunch of others. Then from the digital elevation model, we extracted some information about the slope, so notably the direction, so like is it north facing, south facing, as well as the steepness of the slope, which actually are both very informative about vegetation growth patterns. Yeah, and then we just played around a bit with how to encode the biome information because it's a categorical feature. So yeah, we just played around with a bunch of different ways of doing it. And that also, like all of these approaches individually also gave us a nice performance boost. Most significantly was the slope information, followed by the seasonality and then the different embeddings. And then obviously the next step was to put everything together. And by doing this, we got a very nice performance boost compared to our best performing model from the baselines. Right. However, we still have the underestimation problem because we haven't explicitly targeted that. I mean, we have tried and we have failed, so I'm happy to answer questions about this during the Q&A. But basically, we're still at a point where we have better biomass estimates than the ones that we initially put out with the first paper. So we still feel like we can do something valuable here. And so we went into the direction of kriging or like using Gaussian process regression for specifically spatial correction. And basically what it does is that it allows us from the predictions that we have. So for the sake here of clarity, this is over an entire Sentinel-2 tile. So we have a dense prediction for Sentinel-2 tile as well as associated standard deviations, just because we work with an ensemble of models. So we have associated standard deviations from the predictions. And now we also have the GEDI sparse reference footprints. And what kriging enables us to do is to learn a correction based on the spatially correlated ground truth and the auxiliary standard deviation. Now, actually for the, so first of all, you can also use it without the auxiliary variable. You can also use whatever. Some people have used digital elevation model. But we compared that with the standard deviation because we had the intuition that the model not being certain about the height, the biomass value of something, that could tell a lot about, okay, how strong does the correction factor need to be? So we ran a few experiments for kriging, and if you do it in a naive way, you're actually like going to overfit like crazy to the spatial ground truth that you have. So we spent more time doing this and really understanding what should we do. And now we actually have nice corrected, smoother predictions. But to be honest, I was still working on this morning. So this is work in progress. So if we have any kriging expert here, I'm happy to also have a little chat. But basically what kriging enables us to do is to really drastically reduce, I mean, obviously, because by design, we're now overfitting to the ground truth, but we're now drastically reducing our errors. And what's interesting is that, okay, so the plot, sorry, those are the RMSE bins. So it's a bit, yeah, it's not the most straightforward plot, but basically these are the RMSE bins. So these are all the tiles that have an RMSE that's between 0 and 50. And this in blue are the RMSEs before kriging and in red after kriging. So basically what we see is that for the tiles for which we already have quite a low RMSE, kriging doesn't do much, I would assume, because the remainder of the error is probably also due to the inherent noise in the data. However, as you go into higher and higher RMSEs, then the effect of kriging is drastic. So basically what kriging enables us to do is to take our dense predictions and correct them, so drastically correct the underestimation bias to be much closer to the GEDI ground truth. Now, obviously, this is not scalable because we can only do this for times and locations where we have GEDI footprints. So this is not the way we want to go like in the future. But we thought, okay, we actually have the tool right now to provide better estimates. And so that was something that we wanted to do because if we wait until we're perfectly happy with our biomass estimates to put them out there, I mean, it's going to be a while. We're never going to be perfectly happy with our work. So this can already, to some extent, because kriging also by nature provide uncertainty estimates. We also provide, uncertainties. This can already benefit some people who might want to use those dense estimates, because otherwise the GEDI product is 1 kilometer. So basically we give a better version of the 1 kilometer product. That's actually 10 meters. So yeah, that's what we've been working on right now. Of course, there is a lot of future work to do. This is a tricky topic. So of course, there's actually, like by design, tackling the long tail distribution itself, also implementing uncertainty estimation within the neural network itself, looking into the direction of foundation models. For example, can we get embeddings from them that make us learn more? Or, okay, how do we actually compare to them? Also in the direction of using time series of Sentinel-2 data, because for a given prediction, we only feed one image, and also looking into other encodings of the latitude and longitude, because there's been some interesting work in this realm recently, and many more things, with the end goal, basically, to produce a global map across the years once we're happy with our work. So yeah, before I jump into the Q&A, I just wanted to briefly mention the AI plus Environment Summit, which will take place in Zurich on October 1st. Basically what it is that it's a day-long event. It's in between, it's kind of like a day-long workshop, basically. We have a lot of keynote speakers, pretty cool, some from MIT, some from EPFL, some from ETH and beyond. We also have some parallel sessions that have very specific themes, so like NLP for climate or AI for Earth observation and hazard modeling. We're also going to have a poster session, so if anyone here is interested in submitting their work, that would be great. There will be plenty of opportunities to network and connect. And if we get sufficient funding, we might be able to stream the event online. So in case someone cannot make it, but we would be really happy to see you there, because I think we'd have very nice discussions. So yeah, basically that's it from my side. Thanks a lot for listening, and now I'm happy to take your questions if you have any.
Thank you, Julia. So, questions. I'll start. So the kriging, it helps you with the largest errors. Are those also the ones that are underestimating?
Yeah, exactly. So basically where we get the largest errors is for the largest biomass values. For the small ones, we get small errors, and then in the end, it's small RMSEs. So this is really helping us with the underestimation error.
So very interesting to see that plot, sort of how much does it reduce that underestimation then?
Yeah, but I got those numbers yesterday, so I didn't have so much time to make
that will be later today.
Yeah.
Yeah.
Exactly.
All right, cool. And I mean, you could think about other things with the long tail distribution problem, of course, upsampling and things. Have you explored that?
So basically, so for example, what the Canopy Height paper did is that they had an inverse weighted loss that effectively reduced to some extent the underestimation, but then they also got worse. So they were overestimating the smaller biomass values. So it's a bit of a tricky trade-off, because we want the best of both worlds, right? We want to be able to better estimate the high ones, but we also don't want to sacrifice performance for the small ones, which also translates to worsened performance in general, because there are so many more samples in this bin. But recently I've been like playing around, and something I wanted to do was just because of the way our data set is made. So we have those 25-25 patches. And I thought a very easy way of oversampling the data while not just like just duplicating data samples, but actually augmenting it in a more diverse way would be to just like crop random smaller patches within the 25 patch. And just like oversample some bins according to some, I don't know. I just decided that they should all be sampled the same as this one because as this one because this one doesn't have so much underestimation bias. So I run like a run with this, and what we saw is that we got better at those bins, but then we got worse at this one. So also this was a very naive implementation, but we're looking into it, and it's just a bit tricky to have this trade-off.
For sure. And speaking of the kind of height paper, and by the way, we have a talk by Nico Lang here at Learning Machines that you can check on YouTube. And I mean, how much does the kind of height correlate with the actual biomass estimation?
So it does, but what we've seen is that it's not sufficient. So basically, how I got into this PhD was that I actually did my master thesis on the topic, and another student before me did her master thesis on a similar topic. So she specifically looked into, okay, if we just take Nico's kind of be height map, how well can we estimate biomass? And basically they found that it's doable, but like there seems to be a big room for improvement. So then that was my master thesis, which transformed into this PhD, where we see that canopy height allows us to estimate it, but it also doesn't, like if we add more and more data sources, we get much better at it. So it correlates, but it's also not sufficient because it's a very complex relationship between canopy height and biomass. Like just the height of the tree isn't sufficient. And of course, it's a dense map with its own biases and its own uncertainties. So that also propagates through the estimation process. So there are a lot of things to take care of. And also something I want to do in the future is actually how can I explicitly take into account and not just fitting it as input, the uncertainty in the canopy height map, the uncertainty in the land cover map. So all the uncertainties in my input.
Interesting. Yeah. Do we have questions from the audience? I would like to have a lot of questions on the kriging because I think it's intriguing. But then I'm not that well versed in kriging. But I mean, the kriging, it has some sort of a smoothing aspect, hasn't it?
Yeah, it does. And that's basically what we can see here is that here the smoothing factor, I mean, so the smoothing factor is related to the length scale of the kernel that you use, which defines, okay, how much influence do nearby points have. So you define, okay, beyond a certain radius, then they don't have any effect. And that's the smoothing parameter, basically. And so what you can see here is that the length scale is way too small, so it really leverages neighboring pixels, but it completely, like, it doesn't consider the rest, which makes it overfitting, spatially. Then this one, maybe it's over smoothed. As I mentioned, we're still like working on this.
Mm.
But it's also conceptually interesting because it's kind of it also depends how you yourself pose the problem because it's like, okay, how do you define how you split your data? Do you split them geographically? Do you split them randomly? If you do it geographically, how do you do it? How do you take into account the distance between the points? So that's also something that we're like still pondering, like how exactly do we pose this specific problem to make sure that it makes sense in the end?
Hmm.
So, oh, yeah, open question.
Yeah, and that takes me back to sort of the beginning of your talk when you talked about the different regions and different distributions of different biomes globally, which is of course an interesting problem in all kinds of remote sensing. Um, and I'm not sure I have a question here. It's more like a reflection. It's as you say, it's really how do you state your problem? What is it that we want to generalize to, and sort of where do we have our quality data?
Exactly.
Yeah.
Yeah. And sometimes my professor says, well, we only have one planet, so we can overfit to the entire planet. That's okay.
Yeah.
So yeah, it's really a matter of how you set up the problem.
That's a luxury in remote sensing.
Exactly.
Cool. So thank you very much, Julia, for this exciting talk. We'll be back next week. That will be, I think, May 15th, I think. We'll have Peter Dubin, who is head of Earth System Modeling at EMWF. He'll talk about the digital evolution of the Earth System modeling. So welcome back then, and thank you very much for today.
Thanks for having me. Bye.
Bye bye.